Hello everybody, and welcome back to page 114 in the workbook. So in this video we're going to be looking at two theorems about ring homomorphisms, and let's start with theorem 15.1. It's called Properties of Ring Homomorphisms. If we read the prelude here, it tells us that we're going to let phi from R to S be a ring homomorphism, and then it gives us some other things. A is a subring of R and B is an ideal of S. Okay, now this is a long list of properties. We could read through these. We're not going to do that. I'm gonna kind of leave it to you to read through these properties and to maybe look in the textbook at the proof of some of these. The one point, though, that I'd like to make about this theorem is that it's very similar to Theorem 10.2 back when you talked about group homomorphisms. You might remember there that you defined what a group homomorphism was, and then you had a theorem that gave a long list of properties that every group homomorphism has to have. Okay, as you look through the properties on this list, you're going to notice some definite similarities between the properties here in Theorem 15.1 and the properties that were listed in Theorem 10.2. So you can think of this theorem as just being the analog of Theorem 10.2 for rings. Okay? And let's move down to Theorem 15.2. This one I would like to read through together. Okay, it tells us that kernels are ideals, and specifically, if we read through this, let phi from R to S be a ring homomorphism, it tells us that kernel of phi has to be an ideal of R. Okay, this theorem also has an analog back from chapter 10. In chapter 10, you learned that when you were talking about group homomorphisms, that kernels of group homomorphisms are normal subgroups. Okay, so what we could say is the following, just to draw an analogy here. So ideals are to ring homomorphisms what normal subgroups are to group homomorphisms. Okay, so there's a direct analogy between normal subgroups when we're talking about group homomorphisms and ideals when we're talking about ring homomorphisms. Okay, every kernel is going to be an ideal when we're talking about a ring homomorphism. Just to maybe give you one example of this that we've already looked at, let's scroll back up and look at the example that we did. Okay, let's see. In example 1 up here, we proved that that mapping was a ring homomorphism, and then we calculated its kernel down here at the bottom of the page, and notice what we got. The kernel was the ideal generated by 3. Okay, and the theorem that we were just looking at, okay, Theorem 15.2 tells us that something like that is always going to happen. Every time you look at a ring homomorphism and calculate its kernel, that kernel is going to have to be an ideal.